Okay, let's dive in. We're looking at what the analysis is calling another giant leap from Nvidia, specifically the Rubin CPX Specialized Accelerator.
That's right, announced around September 10th, 2025. And it's not just a chip, is it? It's this whole new rack-scale architecture,
Uh,
Nvidia Rubin, or VR.
Exactly. And for this deep dive, our focus is squarely on you, the investor. What does this highly specialized silicon actually mean for NVIDIA's competitive position and, ultimately, its stock?
Yeah, the mission here is understanding how this shifts the landscape. How does it solidify NVIDIA's dominance? Because the key takeaway really seems to be about total cost of ownership, TCO, efficiency.
And the analysis we're drawing from uses some pretty dramatic language. It suggests this isn't just a step ahead.
No, not at all.
It's its competitors. Think AMD, think custom ASIC providers. They were maybe just starting to get their act together on rack-scale systems.
Finally closing the gap a bit.
And now, they're described as very distant objects in the rearview mirror. That's quite a statement.
It is. The gap in system design is called canyon-sized. That implies, well, it implies that existing non-NVIDIA hardware might be bordering on obsolete almost overnight, at least for certain critical workloads.
Wow. Okay, so what's the core innovation driving this? It's this CPX chip, right?
It is. And what's really interesting, what makes it such a strategic move, is its specialization. It's almost laser-focused on the pre-fill phase of AI inference.
Pre-fill. Okay.
Yeah, it goes heavy on compute FLOPS, the raw calculation power, but it's deliberately, almost ruthlessly skinny on expensive memory bandwidth.
Which is a huge departure.
A massive departure. The research argues this is probably the biggest architectural shift since NVIDIA dropped the GB200 NVL70 Oberon rack back in March 2024. That was already a big leap.
So NVIDIA isn't just making faster chips. They're fundamentally changing the type of chips, forcing everyone else onto a specialized playing field.
Exactly. They're exploiting the inefficiency of using one-size-fits-all hardware for very different AI tasks. That's the competitive angle here. That's the moat they're building.
Okay, to really get why the CPX is such a competitive weapon, we need to talk about the problem it solves, the pain point. And that's this memory wall I keep hearing about.
Absolutely. The memory wall is arguably the defining constraint for big AI models today, especially large language models, LLMs.
Yeah.
It's got two sides. First, capacity. You need huge amounts of high bandwidth memory, HBM, just to load these models with trillions of parameters.
Okay, capacity. Makes sense.
Second, bandwidth. You need incredibly high HBM bandwidth to shovel data in and out quickly. That dictates your token throughput, both when you're training the model and when you're running inference at scale.
And the numbers have just exploded recently, haven't they?
Exploded is the right word. Look at the jump from H100 to GB200. That's less than 3 years. HBM capacity tripled 80 gigs to 288 gigs.
Triple. Wow.
And bandwidth up 2.5 times. 3.3 terabytes per second to 8.0 terabytes per second. That pace is just relentless.
Which has got to put enormous pressure on the actual cost of building these things. The bill of materials, the BOM.
It does. And here's the crucial point for you, the investor. HBM's share of that total package cost has just climbed and climbed. For the GB200, HBM is now the single most expensive component in the package, period.
Okay.
So this rising cost, this HBM wall, isn't just a technical challenge. It's a massive economic problem. And that's the opening for CPX. If HBM gets too expensive for every task,
you find ways to avoid using it where it's not absolutely necessary.
Precisely. You substitute it or you use a lot less of it, especially for parts of the job where it's just overkill.
Which brings us to breaking down the job itself. We can't just think of running an LLM as one monolithic thing anymore.
We absolutely can. Now, if you want efficiency, you have to split LLM serving into two really distinct phases. Phase one is the pre-fill phase.
Okay.
This is where the model takes the user's initial prompt. Could be short, could be pages long, right?
Yeah.
And it processes that whole input sequence to generate just the first token of the response.
That first token. And that impacts the perceived speed, right? The time to first token, TTFT.
Exactly. User experience hinges on that first token appearing quickly. Now, critically, this pre-fill phase, it's almost entirely compute-bound.
Meaning it needs processing power more than anything else.
Yes. It needs raw FLOPS. Lots of calculation to chew through that initial prompt. But here's the key. It barely touches the memory bandwidth once the initial model weights are loaded. The memory is kind of just sitting there during this intense compute burst.
Okay, so lots of engine, not much need for the highway speed yet. Contrast that with phase two.
Phase two is the decode phase. This is what you usually picture the words streaming out one after another.
Generating all the subsequent tokens.
Right. And it's iterative. For every new token, the model has to look back at all the previous tokens it generated. It does this using something called the KV cache.
Okay, the KV cache. Can you give us the quick version of what that is?
Think of it like the model's working memory for this specific conversation. It stores key value pairs representing the context, the meaning of everything said so far.
Got.
So each new token requires reading from and writing to this KD cache, which lives in that expensive HBM. As the output gets longer, the cache gets bigger, and the memory traffic goes way up.
Ah, so that's where the bandwidth becomes critical.
Absolutely. Decode is fundamentally memory bound. It dictates the time per output token, or TPOT. You need massive HBM bandwidth here, or the whole process stalls.
So the analogy holds. Prefill needs the muscle car engine FLOPS. Decode needs the huge, fast data truck HBM bandwidth.
That's a great way to put it. Now think about the inefficiency Nvidia saw. If you run that compute-heavy prefill job on a standard GPU like the R200,
Which is packed with expensive high-bandwidth HBM.
you're paying a premium for that HBM. But the prefill task is barely using it. It's massively underutilized.
Right.
Wasted resources, wasted money.
And that waste becomes a serious drag on profitability, right? Especially
Yeah.
for the big cloud providers, the hyperscalers, particularly when prompts get longer, making prefill take more time.
The analysis puts numbers on it. Running prefill heavy work. Memory bandwidth utilization just tanks. It's pure TCO waste.
How much waste are we talking?
One example cited in the research suggested that using a standard R200 for a task dominated by prefill could waste something like 70 cents per hour per GPU.
70 cents an hour per GPU. That sounds small, maybe.
It sounds small until you scale it. Imagine a data center with, say, 20,000 GPUs, running 24/7.
Okay, yeah, that adds up incredibly fast. That's millions of dollars just evaporating due to inefficient hardware use.
Exactly. It's an unforgivable amount of waste at scale. And that massive TCO pain point, that inefficiency showing up on the balance sheet.
That's the target NVIDIA aimed the CPX at. Fix the TCO problem by building specialized hardware for the specific job phase.
That's the strategic genius of it. Solve the customer's biggest cost headache, and you lock them into your ecosystem for the next hardware cycle.
All right, so the Rubin CPX is the weapon designed to slash that TCO waste. The design brief was basically skinny on memory, fat on compute. How did they actually achieve that? What are the specs?
It really is an object lesson in optimizing for LOPS per dollar. Ruthless cost cutting everywhere else. On the performance side, it delivers 20 petaflops FP8 dense compute.
20 PFLOPS dense.
Yeah, and potentially double that, 40 PFLOPS, using NVIDIA's sparsity techniques. Now compare that the R200, which is a dual-die chip, hits about 44.5 PFLOPS dense. So the CPX offers really strong throughput from a single, presumably cheaper compute die.
But the radical change, the thing that enables the cost savings, is memory. They ripped out the HBM.
They did. Gone. Instead of those expensive complex HBM stacks, the CPX uses 128 gigabytes of GDDR7 memory.
GDDR7, like you find in high-end gaming cards.
Exactly, or professional graphics cards. It's much more commoditized. Now, the trade-off is bandwidth, right? The CPX gets only 2 terabytes per second of memory bandwidth.
Okay, only 2, compared to the R200.
The R200 has 20.5 terabytes per second.
Yeah.
So yeah, a tenth of the bandwidth.
Wow, but that's the point. Prefill doesn't need it.
Prefill doesn't need it. And here's the cost implication, the big one. Switching to GDDR7 cuts the cost per gigabyte by more than half compared to HBM.
50% cheaper per GB.
At least. Combine that lower cost per gigabyte with the slightly lower total capacity compared to R200's HBM options, and the analysis estimates the total memory cost for the CPX package is potentially 5 times lower than the memory cost for an R200 package.
5 times lower, just on memory cost. That's huge. And it doesn't stop there, does it? There are manufacturing savings, too.
Oh yeah. This compounds the advantage significantly. Making chips with HBM like the R200 is incredibly complex. You need advanced packaging, like TSMC's CoWoS process.
Kawa chip on wafer on substrate.
Right. It's basically stacking the HBM dies right next to the main compute die on a special silicon interposer. It involves micro bumps, high-precision alignment. It's difficult.
Which means lower yields, longer manufacturing times, higher costs.
All of the above. It requires very specialized, very expensive, and often supply-constrained manufacturing lines.
And the CPX just sidesteps all that.
Completely. It's designed as a monolithic system on a chip, or fricassee, one single piece of silicon. And it uses a standard conventional BGA package ball grid array.
Like a normal CPU or GPU?
Pretty much. Much simpler, much higher yielding, much cheaper to manufacture, faster time to market too, because it doesn't rely on those bleeding-edge, booked solid CoWoS lines.
Okay, let's recap the investor angle here. Cheaper memory type, 5 times lower total memory cost, and drastically simpler, cheaper manufacturing. All while delivering, what was it, 20 PF/LOPS of dense compute?
That's the package?
Then the sources have to be right. This CPX chip is basically unmatched in maximizing FLPS per dollar spent,
It's designed from the ground up for that metric.
which means Nvidia can offer incredible TCO savings to customers, while potentially enjoying higher margins themselves on the CPX compared to the more complex R200.
That's the beautiful P&L move, isn't it? Address the customer's number one pain point, cost, with a solution that's actually cheaper and easier for NVIDIA to build in some key ways. It's a classic strategic squeeze play against competitors who can't match that specialized efficiency. And it's crucial to understand, the CPX isn't sold in isolation. You don't just buy a CPX chip off the shelf.
Right, it's part of a system, a bigger ecosystem.
Exactly. It slots into the new Nvidia Rubin, or VR, rack architectures. This is the third generation of NVIDIA's integrated rack system following Oberon, and it's slated for 2026.
This really hammers home NVIDIA's strategy, doesn't it? They're not just selling chips anymore. They sell the whole solution: silicon, interconnects, power, cooling, the rack itself, end-to-end control.
Total system control. And with Vera Rubin, they're segmenting the market even further, offering choices based on workload needs.
3 different flavors of these VR racks, is that right?
Yeah, 3 main configurations to let customers dial in their pre-fill to decode ratio and manage TCO. First, there's the baseline, VR200 NVL188. This is purely R200 GPUs, the decode workhorses, 72 of them across 18 trays.
Okay, the all-decode option.
Then, the really innovative one, the VR200 NVL188 CPX. This is the mixed rack. It combines 72 R200 GPUs with 144 Rubin CPX GPUs.
So double the number of CPX chips compared to R200s, a fixed 1-to-2 decode to prefill ratio.
Exactly. Built right in. 8 CPX GPUs per compute tray alongside the R200s.
And the third option gives more flexibility: the Vera Rubin CPX dual rack.
That's the most flexible, yeah. It pairs a standard VR200 NVL188 rack, all R200s, with a second dedicated VR CPX rack that's packed with another 144 CPX refill chips.
Ah, okay, so you buy 2 racks, one for decode, one for prefill.
Right, and this dual rack approach solves 2 big problems for customers. First, flexibility. You can tune your overall prefill to decode or a PD ratio much more precisely based on your specific models, your specific customer SLAs. You're not locked into that fixed 1.2 ratio of the mixed rack.
Makes sense. What's the second problem it solves?
Power and cooling. The analysis highlights that the single mixed VR NVL188 CPX rack is an absolute beast in terms of power consumption.
How much are we talking?
The estimate is around 370 kilowatts per rack.
370 kilowatts. It's nearly half a megawatt for one cabinet of computers.
It's immense, and that requires serious upgrades to data center power delivery infrastructure. Plus, you need extremely capable cooling, likely direct liquid cooling, to handle that heat density. Many older data centers just can't cope with dropping in 370 kilowatt racks without huge, costly renovations.
So the dual rack option lets them spread that power load.
Exactly. 2 racks, likely with lower individual power densities, makes it easier to integrate into existing facilities. It offers a smoother adoption path for customers not ready for that extreme single-rack power budget.
To fit all that compute, you said 396 chips in the mixed NVL188 CPX rack. They must have totally re-engineered the physical layout and cooling.
Oh, absolutely. This is extreme densification.
Wow.
The CPX modules themselves, they're estimated at around 880 watts TDP each. That's a ton of heat.
So liquid cooling is a must.
Direct liquid cooling right at the front of the compute tray for those CPX modules. And the design itself is clever. They talk about a sandwich design.
Sandwich.
Yeah, using both sides of the standard 1U tray height to mount components, likely sharing a common liquid-cooled cold plate running through the middle, packing things in incredibly tightly.
But packing things that tightly, cables must become a nightmare. Reliability issues, airflow problems.
Which is why NVIDIA seemingly abandoned internal flyover cables almost entirely in this generation. That's a huge deal.
No more flyover cables.
Apparently not, or at least greatly reduced. Those cables were a known headache, prone to damage during assembly, signal issues over time, reliability problems under heat stress. Moving away from them is a major engineering feat.
So how do things connect inside the rack then?
The analysis points to a shift towards a cableless design using high-density board-to-board connectors. Things like Amphenol Paladin connectors are mentioned. These connect directly onto a rigid PCB midplane running down the rack.
Like in high-end servers or networking gear. Much more robust.
Much more robust, much more reliable, and it allows for that incredible density, 396 chips in one rack. This architectural change isn't just about performance, it's a massive statement about reliability and serviceability at scale.
Right.
It basically forces competitors to match that level of system integration, which is very, very hard to do quickly.
So the physical rack design itself becomes part of the competitive moat. Better reliability, higher density. It forces an upgrade cycle that only Nvidia is really equipped to deliver right now.
That's exactly it. It locks customers in further based on superior system-level engineering, not just the chip specs.
Yeah.
Okay, so we've got the specialized memory saving money. We've got the simplified packaging saving money. The third pillar of the CPX TCO advantage is networking, or rather, the lack of expensive networking.
Right. This was fascinating. The Rubin CPX chip deliberately ditches NVIDIA's own high-speed proprietary interconnect, NVLink,
Yep, the expensive stuff.
and instead just uses standard PCIe Gen 5, 16 lanes of it, which sounds slow compared to NVLink. Why can they get away with that for a powerful pre-filled chip?
Because of how they structure the computation. It comes down to the software architecture, specifically using something called pipeline parallelism, or PP, for the pre-fill task across multiple CPX chips.
Okay, pipeline parallelism. Break that down. You mentioned an assembly line analogy earlier.
Exactly. Think about building a car. In traditional data parallelism, maybe every worker, GPU, builds a whole car at once, needing access to all the parts all the time. Very communication heavy.
Okay.
In pipeline parallelism, it's sequential. Worker 1, GPU 1, does step A on the car chassis, the prompt, then passes it to worker 2, GPU 2, for step B, and so on down the line.
Ah, so each GPU handles a specific stage of processing the input prompt.
Precisely. And the communication needed is just passing the intermediate result from one stage to the next. It's a simple send-receive operation between adjacent GPUs in the pipeline.
Not the complex all-to-all communication you might need for model training or even the decode phase.
Exactly. The communication overhead for pipeline parallelism is incredibly low.
So for this specific prefill job, the CPX chip is just flat-out compute-bound. It's churning through its stage of the calculation, and the tiny sequential communication step happens almost instantly.
That's the key insight. NVLink, which offers, potentially tens of terabytes per second of bandwidth between GPUs, is complete overkill for this workload. It's totally unnecessary.
And the research backs this up with numbers, comparing the compute speed to the PCI speed.
It does. Even with a demanding model using pipeline parallelism, the CPX's compute limit, how fast it can process tokens computationally, is estimated around 237,500 tokens per second.
Okay, 237.5K tokens per second compute limit.
Now, that basic 16-lane PCIe Gen 5 link, its communication bandwidth limit is equivalent to something like 18.7 million tokens per second.
Wait, 18.7 million versus 237.5 thousand. That's nearly 80 times more bandwidth available on the link than the compute can actually use.
The ratio is huge. The PCIe link is basically sitting idle, waiting for the compute engine to finish its chunk of work. It's nowhere near being the bottleneck.
Which means all that expensive hardware associated with ND-Link, the NB switches inside the rack, the complex optical connections or backplane needed to link them.
It's completely wasted money. Wasted TCO for this specific prefill task. And that's the second massive cost saving NVIDIA is delivering here.
How much does that NVLink infrastructure typically add to the cost per GPU for the customer?
The estimate provided in the analysis is around $8,000 per GPU in total system cost, just for the NVLink scale-up components.
$8,000 per GPU, just eliminated by using PCIe instead for the CPX racks.
Eliminated. That saving goes straight to improving the TCO calculation for the customer buying these specialized racks.
Okay, investor question time. Does NVIDIA pass all that $8,000 saving onto the customer to make the CPX system irresistible, or given the CPX is already cheaper for them to make?
Right. Cheaper memory, no co-OS.
Do they capture a chunk of that $8,000 saving as pure profit margin, further boosting their own bottom line?
I think the smart money is on a combination. They absolutely pass on enough savings to make the customer's TCO calculation a no-brainer, make it incredibly compelling, lock in that market share, make switching away unthinkable.
Okay. Secure the revenue stream.
But yes, given their own reduced manufacturing costs for CPX, they almost certainly capture some of that differential as improved margin. They're reducing the customer's wasted TCO dollars while simultaneously improving their own profitability. It's a very powerful position. They lock the customer into their specialized ecosystem with unbeatable efficiency. #TagVis6. Competitive and supply chain dynamics.
All right, let's pivot to the competition. If CPX is this TCO miracle, what does it do to, say, AMD?
It's Well, devastating is probably not too strong a word. AMD had been making real progress. Their MI300 was competitive. The upcoming MI400 looked promising for rack-scale deployments.
They were closing the gap on Nvidia's previous generation systems.
The analysis suggested exactly that. They were about to catch up on the foundational rack design principles, maybe even had some TCO advantages in certain mixed use cases, and then Nvidia just changed the rules of the game.
By introducing specialization, now AMD can't just compete with a general-purpose GPU anymore.
Not effectively. Not on TCO for these critical prefill workloads. Nvidia has forced them into a two-front war. They now need their own specialized prefill-only chip to compete head-to-head on efficiency.
And why is developing that second specialized chip particularly hard for AMD?
It boils down to resources and market dynamics. Unlike Google, AWS, or Meta, AMD doesn't have massive internal cloud workloads that guarantee demand and provide a huge revenue stream to fund R&D.
They don't have that guaranteed customer zero buying tens of thousands of units.
Exactly. That internal demand acts as a backstop, justifying the huge investment needed to design, tape out, and validate a whole new, highly specialized chip shaped like a prefill accelerator. For AMD, funding that second major GPU development project just to keep pace with NVIDIA's new architecture.
While also needing to improve their main GPU, their interconnect, like Infinity Fabric, their rack system, and their software stack, ROCm.
It puts immense strain on their R&D budget and their profit margins. They're suddenly fighting on multiple fronts against an opponent who just redefined the most important battlefield TCO efficiency for prefill. The analysis suggests this could push AMD's timeline for reaching parity way out, maybe to 2027 or even later.
So a massive setback for merchant competitors like AMD. What about the hyperscalers themselves? Google with TPUs, Amazon with Trainium Inferentia, Meta with MTIA. They do have those internal workloads. Are they now scrambling to build their own CPX equivalents?
They absolutely have the incentive. Maximizing performance per dollar is everything for their internal efficiency. So yes, developing their own prefill-focused silicon makes perfect sense for them. But even they face challenges integrating with NVIDIA's dominant ecosystem if they want to mix and match.
Like the AWS example you mentioned earlier.
Yeah, the AWS integration issue really highlights the stickiness of NVIDIA's system-level approach. AWS loves their custom EFA networking adapters, right? Their elastic fabric adapters.
Critical for their cloud networking.
But the standard VR NVL188 CPX rack is designed around NVIDIA's own Connect X8 NIC, which conveniently includes a built-in PCIe switch function. That integration is tight.
So AWS can't just pull out the Connect X8 and slot in their EFA NIC.
Not easily. The analysis suggests they'd probably have to effectively bypass NVIDIA's integrated networking. They might need a whole separate sidecar rack just for their EFA and ICE.
Whole extra rack.
Yeah, and then they'd need to deploy dedicated PCIe switches, maybe from someone like Astrolabs, just to connect their compute racks to their separate networking rack.
That sounds complex. And expensive, and slow to deploy.
It is. It adds engineering complexity, cost, potentially latency, and definitely slows down their ability to adopt NVIDIA's latest CPX hardware quickly, even for a giant like AWS. It shows how NVIDIA's system design choices create friction for customization.
Okay, let's shift to the supply chain impact. We established CPX uses GDDR7, not HBM. Does this mean doom and gloom for HBM manufacturers like SK Hynix and Micron? If a big chunk of the market shifts to cheaper memory?
It's a valid question, but the economic modeling and the research suggests probably not doom and gloom, more like a shift in dynamics.
How so?
The argument follows classic economic principles, sometimes called Jevons paradox, or in this context, maybe Huang's law, in action. Yes, the CPX systems reduce the share of HBM needed per dollar spent on AI infrastructure, because budget shifts to the cheaper GDDR7 for prefill.
Okay. Less HBM per system dollar.
But the massive TCO improvement achieved by using CPX dramatically lowers the overall cost per AI token generated.
Which makes AI cheaper to run.
Exactly. And when something becomes significantly cheaper, demand for it tends to explode. So the total demand for AI compute, for AI services, goes exponentially.
So the overall market pie gets much, much bigger.
Right. And that massive growth in the total market size usually more than compensates for the lower HBM content per unit. The net result, a higher total dollar market size for the entire AI hardware ecosystem, HBM included. The pie grows so fast everyone still eats well, just maybe the slices are distributed a bit differently.
So HBM demand likely continues to grow in absolute terms, just maybe not as fast relative to GDDR7 for a period.
That seems to be the forecast. And speaking of GDDR7, who wins big from this sudden surge in demand?
Who's best positioned?
The analysis points clearly to Samsung. They were already supplying Nvidia with GDDR for high-end RTX professional GPUs, and crucially, they seem to have the manufacturing capacity, especially for the specific 32 GBP speed bin the CPX likely requires, to meet this massive sudden demand spike.
More so than SK Hynix or Micron?
Apparently, SK Hynix and Micron are heavily invested in and capacity constrained by the booming HBM market. They might not be able to pivot or scale up GDDR7 production as quickly as Samsung, giving Samsung a significant first-mover advantage in capturing this new CPX-driven demand. Hashtag TACCHECK7, future state and final investor takeaways.
Okay, so Nvidia has tackled the compute-heavy pre-fill phase with specialized silicon. The logical next question is, what about the other side, the memory-heavy decode phase?
Exactly. What's the architectural opposite of the CPX? That would be the next frontier for specialization.
A dedicated decode chip. What would that look like?
Conceptually, it would be skinny compute, fat on memory bandwidth.
So like an R200, but maybe with less compute power.
Potentially, yes. You could shrink the main compute die, perhaps remove some cache or specialized units not critical for decode, and focus the silicon budget almost entirely on maximizing HBM capacity and the memory controllers needed to feed it.
And the benefit there from an investor perspective.
Several potential wins. A smaller compute die is cheaper to manufacture, leading to better yields. Lower compute power means lower TDP thermal design power,
Less heat, lower power consumption.
which translates directly into lower power bills and easier, cheaper thermal management for the customer. Yet another TCO improvement lever to pull. This relentless pursuit of specialization seems key to keeping Huang's law, that rapid pace of AI performance improvement, alive.
But before we get to the final wrap-up, we need to touch on the downside of all this specialization for the customer. There has to be a trade-off, right?
There is, and it's flexibility.
Yeah.
Or rather, the lack of it.
How so?
Think about that mixed rack, the VR NVL188 CPX. It comes with a fixed hardware ratio. 72 R200s for decode, 144 CPXs for prefill. That's baked in.
Right, the 1.2 ratio.
What happens if that customer's workload changes significantly? Maybe they deploy new AI models that use much shorter prompts, reducing the need for prefill compute. Or their customer SLAs shift, demanding lower latency during decode, requiring more R200s.
That fixed hardware ratio suddenly becomes inefficient again. They might have too much CPX power sitting idle or not enough R200 power.
Exactly. They lose the ability to dynamically rebalance their hardware resources. They paid a premium for specialized efficiency, but if the workload shifts away from the ratio the hardware was designed for, they could end up right back in an inefficient TCO situation.
That seems like a significant risk. Why wouldn't AMD jump all over that, marketing their general-purpose GPUs as the flexible alternative?
They probably will try. But the reality is, for the huge hyperscale customers driving the market right now, the TCO savings offered by NVIDIA's specialized approach are just too compelling, at least for the near term.
The immediate cost savings outweigh the future flexibility concerns.
For now, it seems so. These big players generally know their workload mix well enough for the next 18-24 months to commit to a fixed, optimized architecture if the price is right. AMD might have a flexibility argument, but they currently can't compete on the sheer efficiency metric that NVIDIA has just redefined with CPX. The TCO gap is just too wide.
Okay, one last technical point before the final takeaways. Sustaining Huang's law. You mentioned specialization, but the industry has also relied heavily on using lower precision numbers, like FP8, to get more throughput. Are we running out of room there?
That's a critical question. We are kind of running out of bits to sacrifice without losing too much accuracy. The analysis specifically mentions NVIDIA talking about Rubin sparsity.
Sparsity, making calculations faster by skipping zeros or unimportant numbers.
Essentially, yes. But the key point is that this Rubin sparsity is supposedly a new scheme, different from the structured sparsity used in Hopper, different from the pairwise sparsity in Blackwell.
So another proprietary NVIDIA innovation.
Seems like it. The details aren't public, but its success is vital. If this new sparsity technique really unlocks significant extra throughput without sacrificing accuracy, it's crucial for continuing the rapid performance gains the market now expects year after year. Without tricks like better sparsity, simply shrinking transistors won't be enough to keep Huang's law going, and the cost performance improvement might start to slow down. So let's bring it all together. What does this Rubin CPX launch, this whole specialization strategy, really mean for the NVIDIA investor?
I think it means Nvidia is playing chess while others might still be playing checkers. They're not just releasing faster chips, they are aggressively redefining the basis of competition.
Moving it from raw FLOPS to system-level TCO efficiency.
Exactly. They're accelerating the entire adoption and obsolescence cycle.
Mhm.
By creating these highly specialized, highly efficient systems like the VR racks with CPX, they make previous generations and competitor offerings look comparatively inefficient and expensive almost overnight.
And by controlling the whole stack, the silicon, the rack design, the power delivery, the cooling, the specialized networking, or lack thereof, they cement that end-to-end control.
Right. They guarantee superior TCO for the customer if the customer buys into the whole NVIDIA specialized ecosystem. It makes it incredibly difficult, technically and economically, for customers to mix and match or switch providers.
So for the investor, this looks like a decisive move to widen that competitive moat significantly. It locks in the biggest customers by solving their biggest cost problems, ensuring NVIDIA remains the primary, maybe the only, viable long-term infrastructure partner for large-scale AI.
Which should translate into robust, defensible, and predictable future revenue streams, justifying that premium valuation investors often place on NVIDIA stock. It's about securing the future by dictating the terms of efficiency today. Hashtag tag a outro. It really is a fundamental shift, an aggressive move defining a whole new benchmark for success in AI infrastructure.
Absolutely. And that leads to the provocative final thought for you, the listener. The arrival of the CPX chip doesn't just change hardware, it changes the metrics. We might see the market shift focus. Instead of just asking, what's the cost per GPU?
The crucial question becomes, what's the cost per prefill token? Or maybe, what's my overall TCO for this specific AI workload?
Precisely. And that forces a hard question onto every competitor, whether it's AMD or Intel or even the hyperscalers building their own chips. How fast can you completely re-architect your silicon roadmap, your system designs, your entire strategy to compete on this new standard of specialized efficiency that NVIDIA just set?
Or do they risk being forced to concede the prefill market almost entirely, becoming niche players focused only on the potentially less profitable memory-bound decode segment, while NVIDIA dominates the critical first step of every AI interaction? That's the multi-billion-dollar question hanging over the industry right now.